Hi, and welcome to Unit 10 Mini Lecture 2 for Astronomy and Astrophysics for Educators. In this lecture, we are going to talk about the existence and basic properties of galaxies other than our own.
So the idea that the collection of stars that we are a part of is not the only collection of stars, that there are other galaxies out there, is actually not that new. The philosopher Immanuel Kant proposed that the universe is filled with great wheels of stars, so-called island universes. Now, in 1845, the astronomer William Parsons identified spiral nebulae. So, for example, M31, M33 are two examples of spiral nebulae that look like this. So this is obviously a collection of something that emits light, but of course we didn't know whether it was within our own galaxy or outside of our own collection of stars. The debate as to whether our galaxy was all there was or whether there existed other galaxies went on for some time, and in particular a debate between two people became known as the Great Debate. Haber Curtis argued that the universe is composed of many galaxies like our own, while Harlow Shapley argued that the spiral nebulae were just gas clouds that were close by, and the universe was composed of only one big galaxy. The issue was settled in 1924. Edwin Hubble measured distances to the brightest spiral nebulae by using Cepheid variables within those nebulae. He identified supergiant stars in the spiral nebulae and figured out that they're so faint that the nebulae themselves must be far outside the Milky Way, therefore settling the issue. So the nearby galaxies to us form what is known as the local group, a loose collection of galaxies that are gravitationally bound to each other. Our local group actually really consists essentially of two big galaxies, the Milky Way and the Andromeda Galaxy, and a collection of satellite galaxies. So these smaller galaxies are essentially orbiting in very elliptical orbits, either the Andromeda or the Milky Way galaxies. So these are kind of like two planets with their own collections of moons. On this two-dimensional projection of the local group, you can see that the distance between the Milky Way and Andromeda is about 2 million light years, or about 600,000 parsecs. As you see here, the closest two galaxies to us are the Small and Large Magellanic Clouds. Here is another view of the local group, which gives you a 3D perspective. This blue disk here is the plane of the Milky Way galaxy. The Milky Way galaxy and the Andromeda galaxy are actually falling in towards each other and will merge in several millions of years. So here is the Andromeda Galaxy, our closest large galaxy. It is a spiral galaxy like the Milky Way. These are the Small and Large Magellanic Clouds, our closest galaxies. You can see that these are not spiral galaxies. They are what are known as irregular galaxies. They have no clear symmetrical structure. Here's another close-up on the Large Magellanic Cloud emphasizing that fact. And again, another view of the Large Magellanic Cloud. Here's the Small Magellanic Cloud, and here's M32, the Pinwheel Galaxy, a satellite galaxy of the Andromeda Galaxy. Okay, so you can see that galaxies come in a variety of shapes and sizes, and those shapes can be categorized. We have spiral galaxies, we have elliptical galaxies. These don't have as much structure as spiral galaxies, and they are roughly spherical or ellipsoidal. And we have irregular galaxies like the Large Magellanic Cloud, which have no shape or structure. So the spiral galaxies are instantly identifiable. So with a good image of a galaxy, it is fairly clear which of those three categories it belongs to. Here we have a nice spiral galaxy. This one is a little trickier to tell because it is side on, but this is a spiral galaxy, as is this. This is an irregular galaxy, and an elliptical galaxy, another spiral galaxy. Now you notice that the spiral galaxies themselves have a range of different shapes. This is an elliptical galaxy, spiral galaxy, side on, another spiral galaxy. So as well as falling into three basic categories, there's also a lot of variation in shape between galaxies. And Hubble came up with a classification system The basic classification system works like this. Elliptical galaxies are designated E, and they're designated E0 through to E6, where E0 is most spherical, E6 is most ellipsoidal. Then S0 is your basic spiral galaxy. The spiral galaxies can be distinguished firstly by whether they have bars in their central bulge, so whether the central bulge of the galaxy is extended in some direction, has a bar-like structure. If they are, then they're designated SB, otherwise just S. And in both cases, there's a subclassification A, B, C, and D, which indicates how tightly wound their spiral arms are, where A is most tightly wound, D is least tightly wound. Now, the distance to the closest galaxies can be measured by observing Cepheid variables in the galaxies. But what about further away when we cannot resolve single stars due to the huge distances involved? We can still measure the properties of the gas that make up the galaxy. In particular, we can still measure 21 centimeter radiation from hydrogen gas that extends throughout any given galaxy. And from the Doppler shifts of the 21 centimeter radiation, we can actually calculate the rotation speed of the galaxy. And this leads to the Tully-Fisher relationship. So the logic goes like this. Kepler's third law says the more massive the galaxy, the faster its rotation rate must be. But if the galaxy is more massive, then it's going to contain more stars, so its luminosity is going to be greater. Therefore, if you can measure the rotation rate, that correlates strongly with the luminosity and will allow you to determine its absolute luminosity. What we see is the apparent magnitude of the galaxy itself, and therefore the distance modulus can be used to obtain the distance to that galaxy. Here's an illustration of that process. Measure the rotation rate. These are typical rotation rates between 30 and 1,000 kilometers per second, and that correlates with the luminosity of the galaxy. This is an actual plot of data of rotation velocities versus absolute magnitude of galaxies, and so you can see they all fit fairly well along this straight line here with a little bit of scatter, so there is some uncertainty in these measurements, but it is relatively small compared to the distances we're measuring. So we can add the Tully-Fisher relationship as the next rung on our cosmic distance ladder. Finally, just to lead us into next week, let me show you some images from the Hubble Deep Field. So the Hubble Space Telescope, during part of its run, focused some very long exposure photographs on a tiny patch of sky close to the Big Dipper, and simply looked at that patch of sky for a long time, collected a lot of light, and measured some of the most distant galaxies in our universe. These are some of the images from it. You see in the tiny patch of sky, you can see hundreds and hundreds of different galaxies of all shapes and all sizes. Here is another image, and this is one of the most recent images from the deep field. A couple of questions that these photographs prompt. Firstly, are galaxies themselves just distributed throughout the universe uniformly, or is there some even larger structure? Do galaxies form into groups of galaxies? We'll talk about that next week. Also, you can see these arcs of light in these pictures, here and here. What are they? Well, as we'll learn next week, these are actually stars whose light has been distorted by the gravitational field of galaxies, of nearby groups of galaxies that are close to our line of sight.